So now we're at the calculus side of inverse trig functions. And, you know, here are your derivative rules. These are the last set that you have to know. You need to know, obviously, everything from Calc 1, product rule, quotient rule, chain rule, logs and exponentials, and here we are with inverse trig. So when I learned these, I was very confused because your derivatives of trig functions are trig functions themselves, meaning, you know, the derivative of sine is cosine. That made sense. This is pretty wild, that the derivative of an inverse sine function is no longer trig. But if you think about that previous video about all of those algebraic expressions, then maybe it's starting to click. Okay, so let me talk about plucking off these rules. Now, this is a screenshot from your textbook, and what they do is they just work the chain rule into everything. So the way that you read this is you would say, well, the derivative of arc sine, the way I view it is I say, and let's just do it down here because this is what I have. If you're going to use the rules, let me execute using the rules. So let's say that. Using the rules. Using the rules above. What I would do to find the derivative is say, like, well, the derivative is 1 over the square root of 1 minus what's inside squared. So see how there's a u there? And that's what it is. And so I kind of think about that u prime being off to the side. I just say, look, there it is. Now chain it. Now multiply by the derivative of x, which is 1. Okay, you're multiplying by the derivative of x, the inside part. Okay, so that's your derivative. And really, like, why do I need to chain it? There's nothing really to chain, so you might as well just lose the 1 and say, hey, here is my derivative. Okay, so that's how you get the derivative using the rules. And we'll practice more of that for sure. Okay, what I want to do is just prove to you why these rules are the way that they are. So I'm going to show you once, and only for arcsine. You could do similar things for arctan and all the other ones, and they're lovely. So I'm going to do this for arcsine. So let me just change color and say, look, here's our equation. So what does this mean? You know, so we've done a couple of things here. What this means, you know, again, arcsine of a value equals an angle. It basically, I can rewrite this by saying sine of y equals x. That's another way of writing y equals arcsine of x. Okay. Again, I took an explicit function of y, equation of y, and made it an implicit equation. Okay, which means I'm going to take the derivative, and I am going to take the derivative implicitly. And that's what's going to prove this. That's why implicit differentiation was so important. Okay, so I'm going to take the derivative implicitly. It's not terrifying. The derivative of sine is cosine. It's y. So because we took the derivative of the y variable, I slapped that dy dx on it. The derivative of x is 1. Doesn't get any better than that. And then to solve for dy dx, all you have to do is divide that cosine y to the other side. Which this is not what you see in the table above, right? I don't see this. I see something with a square root, right? But think about what was in the last video. Let's get after this issue here. We said that the sine of y was x. Let me draw a picture that shows that. Let's draw a triangle. And so I'm going to draw a triangle so like here's the angle is y, which is pretty weird, in a right triangle. Opposite is x. And I don't see anything else. That means hypotenuse must be 1. Let's get an equivalent expression for cosine of y. This is why we need to have that prerequisite skill, right? In order to do the cosine of y, I need it to be adjacent over hypotenuse. I need to know what that adjacent side is. And I can do it because I know that the adjacent squared plus the other leg, x squared, equals the hypotenuse squared. So you can solve for the adjacent side. Again, I'm going to select the positive square root since we were talking about the length of a triangle. And that is my adjacent side, so I'm going to go back into this derivative, right? It's the dy dx here is 1 over cosine y. Well, it's 1 over adjacent over hypotenuse. Well, there it is. You do not have to prove this to me. I'm just showing you where it's coming from. It's a way of utilizing that skill from those prereq problems that were on the previous pages. And I also didn't want you to have a disconnect. You know, why is the derivative to an inverse trig function not trig? You know, why is that? It's because you can replace these trig expressions for algebraic expressions. So certainly, look, I want you to use the rules. No doubt about it. I want you to use the rules. There's a reason I'm giving you this table. It's incredibly helpful. Yes, you need to know this and be able to execute it. I just wanted to show you where it's coming from. If you hated that, don't bother writing it down. It's fine. Don't worry about studying it, let's say. Okay, so let's get into using these rules. And so let's get into the derivative. So here we have arc sine of 2x. I don't want you to like reinvent the wheel and prove everything every time. I'm just going to go right for the derivative. I'm going to make that prime obnoxious there. And remember, the derivative of arc sine, the way I view it is, it's 1 over the square root of 1 minus the inside squared, and then chain it. Okay, so your textbook puts the u prime in the numerator, which really it is. I mean, if this fraction is multiplied by 2, it really is in the numerator. I don't know why I do what I do. What I need you to be careful down here about is that squaring 2x is 4x squared. That's going to bite some of you. Please be careful and be mindful of your algebra work. Okay. Problem number 2. We're going to do arc cosine, okay, of the square root of x. Okay, so here's how this works. I'm going to go right for the derivative. I'm using my rules. The derivative of arc cosine is, the way I view it, negative 1 over the square root of 1 minus what is inside squared, and then chain it. So remember, you're chaining x to the 1/2. That derivative is 1/2 x to the negative 1/2. Let's clean this up here. Again, your textbook just puts this u prime all in the numerator. I kind of tuck it off to the side. It works wonderfully. Everything is fine. So what that means, okay, I'm going to have a 1/2. I have that x to the negative 1/2 is just in the denominator. And then I have the square root of 1 minus, and then just x, because the square root of x squared is just x. This is great. And I don't care if you want to leave it, you know, you can leave it like this. You could write that x to the 1/2 as the square root of x. It's totally up to you. This is great for me. So whatever you want to do. Okay. Again, you do not need to rationalize any of these variables in the denominator. These are appropriately written. I am not forgetting to do that. I do not want you to rationalize. Okay. Yeah. The next two. Okay, well, here I have example number 3, and so, well, we have to make sure that we know our old school Calc 1. This is a straight up chain rule. So what I have to tackle first is that you're taking the derivative of something cubed. So I got to do that general power rule here, right? Bring the 3 in front, reduce the power by 1. Don't mess with the arctan right now. You leave it alone, and then you chain it. So again, using our rules, the derivative of arctan is, the way I view it, I view it as 1 over 1 plus x squared. Now again, I don't have to chain it because the derivative of x is just 1, so I don't really need to write anything in there. This is a great looking derivative. I think handwriting wise it looks okay. I think to be super clear, I'll just rewrite it. I have a tendency of, you know, using a lot of paper and a lot of space. You can tell that from my notes. And some of you may be minimalistic people, but I'll rewrite things just to be absolutely clear that this is that is a multiply. It's not a subtraction. That's not an addition. It's part of the process. Okay. Now you have options on problem number 4. And you can do whichever you want. I think since we're talking a lot about conversion, that is an option for you. You can absolutely rewrite this function if you'd like. You can rewrite and convert to like an algebraic expression. If you'd like to do that, that's legal. We've been talking a lot about these conversions, so I'm going to show you 2 ways of doing it. I guess I'll show you that one first, just to kind of throw this all back in play here. Let's think about it. What does that mean? Well, if I think about that inside part, right, that means I'm going to draw something where the sine of some angle is x over 1. Let's draw a triangle. Here's theta, where the sine is x over 1. This function is the tangent of this angle. So what do I need for tangent? I need to know opposite over adjacent. If I can just find the adjacent length, I have a nice, smooth, equivalent algebraic expression for tangent arcsine of x. Okay, so let's use our skills of doing this. Like, this is kind of cool that you can do that. I can take one leg squared, add it to the other leg squared, and set it equal to the hypotenuse squared. I will solve for the adjacent side. And again, I'm going to be taking the square root and only choosing the positive expression since I have a freestanding triangle. So what you're able to do is say, look, I know that I was presented with this function and it was, g equals the tangent of arcsine of x. You just figured out right now, let me see how much space I have. You just figured out that g of x, let's just rewrite it, is really x over the square root of 1 minus x squared. You just did a little bit of work that you've been working on anyway. And you know how to do the derivative of that. That's a Calc 1 function right there. This is your way around it. You don't have to know the derivative of arcsine of x. It's kind of cool. I can take the derivative just using my old school Calc 1 quotient rule. I haven't talked about that for a while. So let's get in there and do that. You start with the quotient rule. You start with the denominator squared. That's kind of cool because that lifts off the radical. Now, remember the quotient rule, order matters. You have to go bottom. I'm going to write it to a 1/2 power times the derivative of the top minus the top times the derivative of the bottom. And I got to chain it too. That's all in the numerator. Okay. So let's see what this gets me. I don't really need to write the 1 there. I have a double negative here. I have negative x and then a negative 2x, so that's positive 2x squared. Oh, but then the 1/2 is there, so actually I don't even have the 2. That's cool. Okay. And then I have this 1 minus x squared to the 1/2. Oh, negative 1/2. And then the denominator is just 1 minus x squared to the first. Okay, because that's what happens there. Now, this is worth talking about for sure, about like what's going on right here. You can't just drop this negative exponent down because there are 2 terms in the numerator. So what I'm going to do is very quickly, I'm going to get rid of this problem. I'm going to multiply top and bottom by 1 minus x squared to the 1/2 power. That's going to solve my negative exponent issue. I'm going to make sure that this distributes to everybody. The reason I want to use that is because I want to get rid of it from over here. So 1 minus x squared to the negative 1/2 times 1 minus x squared to the positive 1/2. This is where you add exponents. That's 1 minus x squared to the 0. That's just 1. Now when I multiply it to the first guy, that would give me 1 minus x squared to the first. And when I multiply it to the bottom guy, it gives me 1 minus x squared to the 3/2. So when I kind of clean up that numerator, you have 1 minus x squared plus x squared. That's just 1. G prime of x is 1 over 1 minus x squared to the 3/2. Okay. That's one way of doing it. I don't know, kind of nice. You can also go the direct route, so let's write what that would be. Here's your function g of x again. I could say let's just do a derivative. Let's just do a chain rule. Let's get it done. It's a chain rule. It's a fancy chain rule. The derivative of a tangent is secant squared. Remember, you don't mess with the inside stuff now, right? You just sort of chain it out. Now I have to multiply by the derivative of arc sine. So like really that's your derivative. That's just straight up chain. I mean, it's good, but it would be nice if I could make the derivative look a little bit better. Like it would be nice if I could make it equal to that, because these don't even look the same at all. So let's take a little bit of time and let's work on it, right? Let's do that same idea here. We're just utilizing that skill again. Like again, the arc sine of x, very similar to what I just did up above, right? It just means some angle has a sine ratio of x over 1. We already did all the work to find that missing side length. So you could work this out. You could say, look, I just need to know the secant of this angle. The secant of this angle is 1 over the square root of 1 minus x squared. That's one secant. You have secant squared, so you have 2 of them. And then you have this other, like, you know, extra puzzle piece that was just there. I'm just dragging this down. Do you see how it's coming together here? That yes, g prime is the same thing. G prime is 1 over 1 minus x squared to the 3/2. You have 3 of those 1/2 powers. You add exponents here. So that's 1 minus x squared to the 1/2 times 1 minus x squared to the 1/2 times 1 minus x squared to the 1/2. And that gives you 1 minus x squared to the 3/2. You see they're the same. It's up to you what you want to do. But it would be nice to get rid of this big hunk of mess over here of what that derivative would be. Okay. Okay, so what else do I have up my sleeve? Oh, let's put some meaning to it, right? Like here's our last example. Thank goodness. Oh my goodness. You know, inverse trig. Look, I don't want you to forget about your Calc 1 skills. You can't pass Calc 1 without writing the equation of a tangent line, and we write them in Calc 2 as well. So I'm going to refresh your Calc 1 skills as much as possible, and if you need more refreshing, then you let me know. But when you're doing the equation of a tangent line, you need 3 things. You need an x value, which was given. You need a y value, which I can find. I just have to plug into the function. Okay, and I need a slope value, which is just plugging into the derivative. Like that's it. Like those are your 3 pieces. They gave you 1 out of 3, and you have to go fishing to find the other 2. Now they gave you the function, so I guess I'll just plug in there. Okay, so I have to know off the top of my head that e to the 0 is 1. And here's why you need to know how to evaluate inverse trig, because you have to know what arctan of 1 is. You have to just know that that's pi over 4. That is pi over 4 is the angle that gives you a tangent ratio of +1. That's the only answer, by the way. It has to be pi over 4. It can't be 5 pi over 4. It's got to be in the allowable angles that you're permitted to answer. So look, your value of the function here is pi. Okay. Now, your slope, let's think about it. Your slope is the derivative. So let's do that. Where do I want to do that work? I guess I'll just do f of x here. F prime. Okay, so the derivative of arctan, remember, is 1 over 1 plus what's inside squared, and don't forget to chain it. The derivative of e to the 3x is e to the 3x times 3. That's a mouthful right there. Now, just for the sake of doing it, I'm going to kind of throw all this together. Let's talk about good mechanics. You multiply exponents in here. That's f prime of x. I want f prime of 0, right? So that means I'm going to plug a 0 in. What is that? 12 times e to the 0 over 1 plus e to the 0, otherwise known as 12 over 2, which is 6. You have all the little nuggets of information that you need to write the equation of the tangent line. You have the x value, the y value, and the slope. Let's do it. So, y value, is pi. Slope is 6. X value is 0. This looks great. I accept that. That is an equation of a line. It's point slope form. You might be horrified and traumatized. You might want to actually distribute the 6 through and say your answer is 6x plus pi. They're equally lovely. They're equally perfect. Thanks, guys.